The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So a couple of things I want to say about the final project. You guys should start thinking about it. And so of course, you guys should think about the teams first and submit team information, saying who you are going to team up with, by when, team information. Josh, by when? Team information has to be in.
By tomorrow.
By tomorrow, okay, good. You should know your teams, get them together, use the same mechanism that we used before to get the team information before. So we are going to add one small thing this year. I think that would be useful. Once you have submitted your design documents, we are going to get a design review done by masters. So what that means is next week, we are going to schedule a design review with your masters, and you should send mail to your masters, hopefully some middle of next week, to schedule a design review. Design review will happen the week after Thanksgiving. So you'll submit your design doc next week, and then week after Thanksgiving, you'll schedule a design review. Earlier the better, because you can hopefully get some really good feedback before you go into implementation. So have an idea what you're doing. Of course, you'll write it up for your design document, and then go with your masters and say, here's what I'm planning to do, get some good feedback, and hopefully it will help your life to do that. And then, beforehand, performance only mattered for your grade. We did this absolute grading. This year, we are going to have actually in-class competition on the final day of class to figure out who has the fastest ray tracer in the class. And for that, we will actually give a user a little bit of a different image than what I have given you. And so you don't go too much into really hand code into that image, because that might not work. And so here's something hot off the press. So for the winning team, there's going to be an Akamai prize for the winning team. And this prize includes a celebration demonstration at Akamai headquarters. You'll go visit their NOC and perhaps show off to their engineers the cool ray tracer you did. And also, every team member in the winning team is going to get the iPod Nano. Okay? Sorry, guys, last year it didn't happen. First time. Okay, so there's a lot at stake. So make sure your program is going to run as fast as you can. Okay, with that. Okay, let's get your slides on. So I'd like to introduce Bradley Kuszmaul. Bradley has been at MIT, in and out of MIT for a long time, doing a lot of cool stuff with high performance. Yeah, make it bigger, screen bigger. High performance computing. He has done some really interesting data structure work, high performance optimizations work, and stuff like that. And today he's going to talk about interesting data structure that goes all the way from theory into getting really, really high performance. Thank you, Bradley. Okay, you have the mic.
So I'm going to talk about a data structure called fractal trees, which in the academic world are called streaming Btrees, but the marketing people didn't think very much of that. And so a lot of these slides are borrowed from a company that I've started. So rather than redo that, I'm just going to stick to the terminology fractal tree. I'm research faculty at MIT, and I'm a founder at Tokutech. And so sort of who I am, I'll do a little bit more introduction. So I've been around at MIT a long time. I have 4 MIT degrees. And I was one of the architects of the connection machine CM5, and that was work that Charles was also one of the architects of that machine. So at the time, that was the fastest machine in the world, at least for some applications. And after getting my degrees and being an architect, I went and was a professor at Yale, and then later I was at Akamai. So I don't know an Akamai prize is be on an iPod, but maybe it's like all your content delivered free for a month or something. And I'm now research faculty in the SuperTech group working with Charles. And I'm a founder of TokuTech, which is commercializing some work we did. A couple of years ago, I started collaborating with Michael Bender and Martin Farish-Colton on data structures that are suited for storing data on disk. And we ended up later starting a company to commercialize the research. And basically, I'll tell you what it's, sort of what the background is, and actually go into some technical on the data structure. So I don't know exactly what you spent most of your time on, but a lot of high performance work, especially in academia, focuses on the CPUs and using the CPUs efficiently, maybe getting lots of flops or something. The Silk work that Charles and I did, for example, is kind of squarely in the category of how do you get more flops or more computrons out of a particular machine. But it turns out often I/O is a big bottleneck, and so you see systems that look a little bit like this. You have a whole bunch of sensors somewhere, and the sensors might be something like a bunch of telescopes in an astronomy system. They're sending millions of data items per second, and they have to be stored. And disk is where you have to store large amounts of data, because disk is orders of magnitude cheaper per byte than other storage systems. And then you want to do queries on that data, and the queries you want to look at the data that's recent. So it's not good enough just to look at yesterday's data. You want to know what's going on right now. If your sensor array is a bunch of telescopes and a supernova starts happening, you want to be able to find out quickly what's going on so that you can broadcast a message to everybody in the world so they can all point their telescope at the supernova while it's fresh. So that's sort of the picture. Another example of a sensor system is the internet, where you have thousands or millions of people clicking away on Facebook, for example. You could view that collection of mice as abstractly a bunch of sensors. And so it's, you see it in science, you see it in internet, there's lots of applications. For example, another one would be that you're looking for attacks on your internet infrastructure in a large corporation or something. So trying to reduce this big sensor system to sort of, what is the fundamental problem? Basically, we need to index the data. So the data indexing problem is this. Data is arriving in one order, and you want to ask about it in another order. So typically, data is arriving, it's, in the order, by time, right? An observation is made, the event is logged, and the next observation is made, the event is logged. And then you want to do a query. It's like, tell me everything that's happening in that particular area of the sky over the past month. So there's kind of a big transposition that has to be done for these queries abstractly, as the data's coming in one order, and you want to sort it and get the data out in another order. So one solution to this problem that a lot of people use is simply to sort the data. The data comes in, sort it, right? Then you can query it in the order that it makes sense. This is basically a simple-minded explanation of what a data warehouse is. A data warehouse is all this data comes in. Walmart runs one of these in Arkansas. All these events, which are people scanning cans of soup on barcodes all over the country out in Walmart stores, all that data arrives in Arkansas in one location. They sort the data overnight, and then the next morning they can answer questions like, what's the most popular food in the week before a hurricane strikes? When you've gotten, because this is a kind of request that Walmart might care about, because they get a forecast that a hurricane's coming, and it turns out they need to ship beer and blueberry Pop-Tarts to the local stores, which are the things that basically you can eat even if power has failed. The problem with sorting is that you have to wait overnight. And if you're, for Walmart, that might actually be good enough, but if you're the astronomer, that application, it's not so great. So this problem is called the indexing problem. We have to maintain indexes. And the solution is to use, traditionally, the classical solution is to use a data structure called a Btree. So do you all know what a Btree is? took data structures for algorithms. Btree is like a search tree, except it's got some fan out, and I'll talk about it in a second. They show up in virtually all storage systems today, and they were invented about 40 years ago. And they show up in databases such as MyISAM or Oracle. They show up in file systems like XFS. You can think of what Unix file systems like ext do as being a variation of a Btree. Basically, they're everywhere. Mike drew this picture of a Btree, and I said, I don't get it. He said, well, you know, there's a tree and there's bees. And I said, but those are wasps. So anyway. So Btree looks like this. It's a search tree, so that means everything, you know, this is organized as, you know, it's got left children and right children, and there's actually many children. And like any other search tree, all the things to the left are before all the things to the right. That's sort of the property of trees. It lets you do more than just a hash table. A hash table lets you do get and put, right? But a tree lets you do next. And that's the key observation that why you need something like a tree instead of a hash table. A lot of database queries. If you go and click on Facebook on, you know, somebody's page, there's all these things that have been posted on on somebody's wall. And what they've done when they organize that data is that they've organized it so that each of those items is a row in a database, and they're next to each other, so that you fetch the first one, which is like the home page of the person, and then the next and next gives each of the messages that they want to display. And by making those things adjacent to each other, it means that they don't incur a disk I/O every time. You know, if it were just a hash table, you'd be having to look all over the place to find those things. So Btrees are really fast if you have to do insertions sequentially. And the reason is sort of you have a data structure that's too big to fit in main memory. Otherwise, if the data structure fits in main memory, this is just the wrong data structure, right? If it fits in main memory, what should you use to solve this problem? Any ideas? What data structure is like a Btree, except it doesn't have lots of fan out? Does anybody know this stuff in this class? Do you people know data structures at all? Is that, maybe I'm in the wrong place, because it's okay, you know? Just a binary tree would be the data structure if you were doing this in memory, right? Because a binary tree would be fine. Or maybe you would try to minimize the number of cache misses or something. So for sequential inserts, if you're inserting at the end, basically all the stuff down the right spine of the tree is in main memory, and an insertion just inserts. You have no disk IOs, and basically it runs extremely fast. It's the disk IO is sequential. You get basically performance that's limited by the disk bandwidth, which is the rate at which the disk can write consecutive blocks. But Btrees are really slow if you're doing insertions that look random. The database world calls those high entropy. And so basically the idea is I pick some leaf at random, and then I have to bring it into main memory, put the new record in there, and then eventually write it back out. And because the data structure is spread all over disk, then each of those random blocks that I choose, when I bring it in, that's a random disk IO, which is very expensive. So here, for this workload, unlike the previous workload, the disk performance, the performance of the system is limited by how fast can you move the disk head around rather than how fast can you write having placed the disk head. And that's, you end up perhaps you can only on a disk drive do something like 100 disk head movements per second. And if you are writing small records that are like 100 bytes or something, you might find yourself using 0.001% of the disk IO, of the disk's bandwidth performance. And so people hate that. They hate buying something and only being able to use 0.001% of its capacity, right? New Btrees. Something's wrong with that title. So Btrees are really fast at doing range queries, because basically once you've brought a block in, you want to do the next item. The chances are the next item's also on the same page, so once in a while you go over a page boundary, but mostly you're just reading stuff very fast. Oh, I know what this is about. When a Btree is new and it's been constructed sequentially, it's also very fast. When it gets old, what happens is the blocks themselves get moved around on disk. They're not next to each other. And so this is a problem that people have spent a lot of time trying to solve, is that as Btrees get older, their performance degrades. This aging problem, I saw one report that suggested that something like 2% of all the money spent by corporations on IT is spent dumping and reloading their Btrees to try to make this problem go away. So that's a lot of money, or pain or something. Well, Btrees are optimal for doing lookups. If you just want to look something up, there's an old argument that says, gee, if you're going to have a tree structure, which is what you need in order to do next operations, then you're going to have some path through the Btree which is, a certain depth, and you do optimally by having the fan out be the block size, and everything works. So but that argument of optimality is not actually true for insertion workloads. And this is sort of where the data structures work that I've done with Mike and Martin sort of gets to be an advantage. To see that Btrees aren't optimal for insertions, here's a data structure that's really good at insertions. What is the data structure? I'm just going to append to the end of a file, right? So it's great. Basically, it doesn't matter what the keys are. I can insert data into this data structure at disk bandwidth, right? What's the disadvantage of this data structure? Lookups. So what is the disadvantage? Like, it's not, lookups aren't so good. What do you suppose, what is the cost of doing a lookup? Order n. Yeah, you have to look at everything, right? It requires a scan of the entire table. And we'll get into what the cost model is in a second, but basically you have to look at everything. So to first, it's order n. It turns out the number of blocks you have to read in which is the thing you care about, it's order n over b, which is, so we'll get into a performance model in just a second. So here we are. We have two data structures, Btree, which is not so great at insertions. It's quite good at point queries and quite good at range queries, especially when it's young. And we have this other data structure, which is the append data structure, which is wonderful for insertions and really bad for queries. So can you do something that's like the best of all possible worlds? You could have imagined a data structure that's the worst of all possible. But it turns out that there are data structures that do well for this, and I'll show you how one works in a minute. So to explain how it works and to do the analysis, we need to have a cost model. And we got into this just a minute ago with what is the cost model for a table scan. Is it order n? Well, if you're only counting the number of CPU cycles that you're using up, it's order n, because you have to look at every item. But if what you really care about is the number of disk IOs, then you just count up the number of blocks. And so in that model, the cost is order n over b. And that's the model that we're going to use to do this analysis. So in this model, we aren't going to care about CPU cost. We are going to care about disk IO. And that's a pretty good place to design in if you're an engineer, because right now, the number of CPU cycles that you get for $1 is going up. It's been going up. It's continuing to go up. You have to write parallel programs today to get that. But you get a lot of CPUs, a lot of cycles in a $100 package. But the number of disk IOs that you're getting is essentially unchanged. It's maybe improved by a factor of 2 in 40 years. So that's the one to optimize for, is the one that's not changing, and use all those CPU cycles if you can to do something. So the model here is that we're going to have a memory and a disk, and you could use this in and blocks move. There's some block size B which we may or may not know what it is, and it's actually quite tricky on real disk systems to figure out what the right block size is. It's not 500 bytes, right? Because that's not going to be a good block size. It might be more like a megabyte. And when we move stuff back and forth, we're going to move a block at a time. We're going to bring in a whole block from disk, and when we have to write a block out, we write the whole block out. So we're just going to count that up. There's two parameters. There's the block size B and the memory size M. So if the memory is as big as the entire disk, then the problem goes away. And if memory's way too small, like you can only have one block, then it's very difficult to get anything done. So you need to be able to hold several blocks worth of storage. The memory is treated as a cache for disk. So we're going to, once we've brought a block in, we can keep using it for a while until we get rid of it. So have you guys done any cache-oblivious data structures? OK. So you've seen this model, right? So the game here is to minimize the number of clock cycles and not worrying about the CPU cycles. So here's the theoretical results. We'll start with a Btree. So a Btree, which has block size B, and here I'm going to assume that the things you're storing are unit sized, because you can do the analysis, but it gets more complicated. So the cost of a lookup, which is the upper right side, is log n over log b. That's the same as when you're not, you may not be used to manipulating these, but usually people write this as log base b of n, but that's the same as log n over log b. And I'm going to write it this way because then it's easier to compare things. So if b is 1,000 or something, then basically instead of paying, if n is, just as an example, if n is say 2 to the 40th, so log n is, convert these all to LGs because it basically doesn't matter. So it's 40 over log base b, and if b is say 2 to the 10th, then that means that if you have 1 trillion items and you have a fan out of 1,000, it takes you at most 4 disk IOs to find any particular item, right? And insertion cost is the same, because to do an insertion, we have to find the leaf that the item should have been in and then put it there. So the append log, well, what's the cost of insertion? Well, we're appending away, right? And once every B items, we actually have to do a disk IO. So the cost of an insertion in the append log, it isn't 0. It's one bth of a block IO per object. And the point query cost looks really bad. It's n over b, which we already discussed. So the fractal tree has this kind of performance. It's log n over, it's not b, which would be really great. It's something smaller. It's like maybe square root of b. And for the insertion cost, and the lookup cost is log n over something, which I'm going to just hide. Let's set epsilon to half and work out what that is, because epsilon half is a good engineering point. So the insertion cost is log n over b to the 1/2, which is log n over root b, right? And the other one, the lookup cost, is, there's all big O's around here, but I'm not going to draw those again, over half, so I'm going to maybe ignore that, of the log of the square root of b. Did I do that right? B to the 1 minus half. Put the 1/2 back in to make you happy. So big O of that. Well, what's the log of root b? I can't quite hear you, but I know the answer. Right? I can just say that's the same as log b when I'm doing big O's. Get rid of the halves, so it's log n over log b. So if you sort of choose block sizes, which are, if you set this parameter to be something where you're doing something the square root, you end up having lookups that cost asymptotically the same as for a Btree. although there are these constants in there. There's like a factor of 4 or something that I've glossed over. But asymptotically, it's the same. And lookups or insertions have this much better performance. What if, if B was 1,000, then we're dividing by 30 here. But B isn't really 1,000. B is more like a million in a modern system. So you actually get to divide by something like 1,000 here. And that's a huge advantage, to basically make insertions asymptotically be 1,000 times faster, whatever that means. When you actually work out the constants, perhaps it's a factor of 100, is what we see in practice. So this is basically working out those details. And so here's an example. Here's a data structure that can achieve this kind of performance. It's a simple version of a streaming Btree or a fractal tree. And what this data structure is, so first of all, is everybody ready to kind of switch modes from, marketoid, or at least explaining what it's good for, to talking about what a data structure is that actually solves the problem. So any questions before we dive down that path? Okay. So if there are any questions, stop me, because I like to race through this stuff if possible. So the deal here is that you're going to have log n arrays, and each one is a power of 2 in size. And you're going to have one for each power of 2. So there's going to be one array of size 1, one of size 2, one of size 4, and 8, 16, all the way up to up to 1 trillion, right? 2 to the 40th. The second invariant of this data structure is each array is either completely full or completely empty. And the third one is that each array is sorted. So, do an example here. If I have 4 elements in the array, these are the numbers, there's only one way for me to put those in that satisfy all those requirements, right? Because there's 4 items, it has to go into the array of size 4, it has to fill it up. I can't have any other way of doing that. And within that array of size 4, they have to be sorted. So those 4 elements uniquely go there, and that's the end of the story for where 4 elements go. If there's 10 elements, you get a little freedom, because, well, we have to fill up the 2 array and we have to fill up the 8 array, because there's only one way to write in binary 10, which is 0, 1, 0, 1. But we get a little choice. It turns out that the bottom array has to be sorted, and the top array, the array containing 5 and 10 has to be sorted, but we don't actually, we could have put the 5 down here and say swap the 5 and the 6, and that would have been a perfectly valid data structure for this set of data as well. So we get a little bit of freedom. Okay? So that's the basic data structure. So now what do? How do you search this data structure? Well, the idea is just to perform a binary search in each of the arrays. The advantage of this is it works, and it's a lot faster than a table scan. The disadvantage is it's actually quite a bit slower than a Btree, because if you do the analysis here, which this class you've done things like master theorem and stuff, right? So you know what the cost of doing the search in the biggest array is, right? How many disk IOs is that in the worst case? It's log n. It's going to be log base 2 of n, right? Plus or minus a little bit. Just ignore all that stuff. I'll just do log. So what's the size of doing the second biggest array? What's the cost of searching the second biggest array? It's half as big. So it's log of n over 2, right? Can't write. So this is log n. This is equal to log of n minus 1. What's the next array? What's the cost of searching the next biggest array? Log of n minus 2. And you add that up, and what's the sum? Don't even need recurrences for this. Could have done it that way, but what's the sum when we get down to 1, right? You search the bottom array, you have to do a disk I/O in the one disk I/O in the worst case. So this is an arithmetic sequence, right? So what's the answer? Big O. I'm not even going to ask for the, Pardon? Yes, it's log squared, which is right there in green. So you basically, this thing's really expensive. Log squared n, when what we were trying to get, we were trying to match a Btree, which is log n over log b. So not only is it not log base b, it's log base 2 or something, but it's squaring it. So if you think of having 1,000,000 items in your data structure, it's even a relatively small one, right? Log base of 1,000,000 is 20. You square that, that's like 400. Maybe you get to divide by 2. It's hundreds of disk I/Os just to do a lookup instead of 4. So this is just sucking at this point. So let's put that aside and see if we can do insertion since we are doing so badly at logging. So to make this easier to think about, I'm going to add another set of temporary arrays. So I'm actually going to have 2 arrays of each size. And the idea is at the beginning of each step, after doing an insertion, all the temporary arrays are empty. And I'm only going to have arrays on the left side that are going to have data in them. So to insert 15 into this data structure, there's only one place to put it. I put it in the 1 array. If I'm trying to be lazy about how much work I want to do, and it turns out this is exactly what you want to do. You just you have an empty 1 array, a new element comes in, just put it in there. Now I want to insert a 7. There's no place in the 1 array, so I'm going to put it in the 1 array over on the temp side. And then I'm going to merge the 2 1 arrays to make a 2 array. So the 15 and the 7 become 7 and 15 here. I couldn't put it there because that array already was full. And then I merged those 2 to make a new 4 array. So this is the final result after inserting those 2 items. That makes sense? It's not a hard data structure. So one insertion can cause a whole bunch of merges. Here we have sort of an animation. So here I've laid out the 1 array across the top, and then the temporary array just under it. And then going down, we have a sequence of steps, one for the data structure over time. So we have the whole arrays, we have the 1 and the 2 and the 4 and the 8 array are all full. And we insert one more item, which causes a big carry. So the 1 creates a 2, the 2 2s create 2 4s, the 2 4s and the 8 create 2 8s, and so forth. So here you are, you're running. You've built up a terabyte of data, right? You insert one more item, and now you have to rewrite all of disk. So that also sounds a little unappealing. But we'll build on this to make a data structure that actually works. So first, let's analyze what the average cost for this data structure is. I've just sort of explained why there are some really bad cases where you're doing an insertion and it's expensive, but on average, it turns out it's really good. And the reason is that merging of sorted arrays is really I/O efficient, because the merge is essentially operating on that append data structure. We're reading 2 append data structures and then writing the answer into another append data structure, and that's hardly any I/O. So if you have 2 arrays of size x, the cost to merge them is you have to read the 2 arrays, you have to write the new array. And you add it all up, and that's order x over b I/Os. Maybe it's 4x over b or something, but big O of x over b. So the merge is efficient. The cost per element for the merge is 1 over b because order x elements were merged when we did that, and we get to spread the cost. Sure, we had to rewrite a trillion items when we filled up our disk, but we actually were, when you divide that out over the trillion items, it's not that much cost per item, and that's so the cost for each item of that big operation is only 1 over b disk I/Os. And each item only has to be rewritten log n times. So the total cost, the total average cost for an insertion of one element is log n over b, which is actually better than what I promised here, but this data structure is going to be worse somewhere else. So this is a simplified version. I'll get to within, ignoring epsilons and things, it'll be good enough. So does that analysis make sense? It's not hard analysis, so if it doesn't make sense, it's not because of you, it's got to be because I didn't explain it, because it's too easy to not understand. But it's, so now we have to do something about if you're going to build something like this, you can't just say, oh, well, your database is great, except once every couple days, it hangs for an hour while we resort everything. So the fix of this is that we're going to get rid of the worst case. And the idea is, well, let's just have a separate thread that does the merging of the arrays. So we insert something into a temporary array and just return immediately. And as long as the merge thread gets to do at least log n moves every time we insert something, it can keep up. You could actually do a very careful kind of dance where I insert something, and part of the insertion is I have to move something from this array and something from this array and something from this array, and I can keep everything up to date that way. So it's not very hard to de-amortize this algorithm. That is, to turn the algorithm from a good average case behavior to good worst case behavior. The worst case behavior just becomes that it has to do log n work for an insertion, which isn't so bad. Does that make sense? Yeah. Well, okay, so the question, let me repeat it and see if, so you're in the middle of doing these merges, and you have a background thread doing that, say, and somebody comes along and wants to do a query. So the trick to there is that you put a bit on the array that says the new array is not ready to query, keep using the old arrays, which are still there. Just don't destroy the old ones until the new one's ready. So basically you have these 2 megabyte size things, you're trying to make a 2 megabyte size one, you leave the 1 megabyte ones lying around for a while you're incrementally moving things down, and then suddenly when the big one's done, you flip the bits. So in order 1 operations, you can say, no, those 2 are no longer valid and this one's valid, so queries should use this one instead of those. So that's basically the kind of trick you might do. Or you would just search the partially constructed arrays if you have locks. There's lots of ways to do it. That's a pretty good question, yes. That's one that we had to think about a little. So it sounds glib, but it's like, how do we do this? Any other questions? Okay. So now we got to do something about the search, because the search is really bad. Well, it's not as bad as the insertion worst case thing. I'm going to show you how to shave off a factor of log n, and I don't think I'm going to show you how to shave off the factor of 1 over log b. So we'll just get it down to log n instead of log squared n. Then because if I actually want to get it down, then I have to give up. Remember, the performance that I had was log of n over b. If I actually want to get rid of things, I have to do something else. There's a lower bound argument. So the idea here is we're searching. I'm going to flip those. We've got these arrays of various sizes. And I've just done a binary search on here, and then here, and then here, and I found out the thing I'm looking for wasn't here, and it wasn't here, and it wasn't here. That's where it would have been if I had wanted, if it had been there. It should have been there, but it wasn't. It should have been here, but it wasn't. And then I'm going to start searching in this array. And the intuition you might have is that, gee, it's kind of wasteful to start a whole new search on this array when we already knew where it wasn't in this array. Right? So for example, if the data were uniformly, randomly distributed, and the thing was, say, 1/3 of the array here, I might gain some advantage by sort of searching at the 1/3 point over here to see if it's there. Now, that's kind of an intuition. I don't know how to make that work, but I do know how to make something work, okay? But the intuition is, having done some search here, I should, in principle, have information about where to limit the search so I don't have to search the whole thing on the next array. Okay, and here's basically what you do, is every element, you get a forward pointer to where that element would go in the next array. So for example, you have something here and something here, which are the two things that are less than and greater than the thing you're looking for, and it says, oh, those should have gone here in the next array. So if you maintain that that information, it's almost enough, but let's gloss over the almost part. If those two destinations of those two pointers are close together, then you've saved a lot of search in the next array, right? Does anybody see a bug in this? There is one, the almost part. You don't have to see it, because I've been thinking about this a lot, and The problem is, what if all of these items are less than all of these items, for example, right? In which case, these pointers all point down to the beginning, and we've got nothing. That's a case where this fails, and that's allowed, right? If we, in particular, if we were inserting things sort of, yeah.
Then we know the element isn't the biggest, right? Because the element was supposed to go between the two.
But in this array, we found out that it's above the last element when we did our search, right? That's one of the possible ways that the worst case behavior is, we've got something where this array is less than this array, and we're looking for that item, so we do a binary search and find out it's over here. And it doesn't help to special case this or something, because they could be all to the right, or they could be all bunched up in funny ways. There's lots of screwy ways that this could go wrong. But this simple version, it's easy to come up with an example, which is everything's to the left. Yeah?
Well, I mean, you still save time by, like, when you do the binary search of the smallest array, that gives you pointers into the next one, which you can search at a reduced cost, which gives you the next one, and so on.
So there is a way to fix it so that the pointers in the smaller array do help you reduce the cost in the next array. And that is to seed the small array with some values from the next array. Like, suppose I put in every 20th item and I stuck it in that array with a bit on it that says, oh, this is a repeat, it's going to be repeated again. So then I could guarantee that there's these dummies that I throw in here which are evenly spaced, plus whatever else is in there. So put the other things in there, and those, they have forward pointers too. And now I'm guaranteed that the distance between two adjacent items is guaranteed to be a constant. Does that make sense? It's kind of, the trick is to make it so that having found two adjacent items, that the thing you want, that on the next array, that the sort of the image of those two items is separated by at most 20 items. And so that gets you down to only log of n instead of log squared of n, because there's just, you're searching constant items in each array, and there's only log n arrays. Yeah?
Doesn't that slow down the merging of arrays?
Not asymptotically, right? Because asymptotically, what this means, if I'm going to build that array, so I'm going to merge two arrays to make this array, I have to do an additional scan of this other array as I'm constructing this one. So the picture is I have two arrays, and I'm trying to merge them into this array, and I'm trying to also insert these dummy forward pointers from the next array, which is only twice as big. So the big O's are, it's like, if it's x, instead of it being 1, 2, 3, 4x, it's 8x. So it's only a constant, right? So basically, I can read all three of these. I can read an array and the next one, and the next array, which is twice as big, and the next array, which is 4 times as big. It all adds up to 8 times the size of the original array. So at least the asymptotics aren't messed up. Maybe the engineer in you goes, bleh, I have to read the data 8 times. But But remember, the game here is not to get 100% of the disk's insertion capacity. That's not the game, going back to sort of the marketing perspective. The competition is only getting 0.001% of the disk's capacity, right? That's what a Btree gets in the worst case. And so we don't have to get 100% to be 3 orders of magnitude better, which is where we are. We only need, so it turns out that for this kind of things, we end up getting like 1% of the disk's capacity, and we're, everybody's jumping around saying, that's great, because it's 1,000 times faster. And so, and why do we only get 1%? Well, there's a factor of 2 here and a factor, and there's a log n over there, and it's like you divide all that, and it's a constant kind of a challenge because the engineers at Tokutech always are having ideas for how to make it faster. And right now, making this data structure faster is not the thing that's going to make people buy it, because it's already 1,000 times faster than the competition. What's going to make it faster is some other thing that adds features that make it so it's easy to use. So I keep having to sort of, no, you really need to work on making it so that we can do backups or something. That's, turns out, if you're selling a database, you need to do more than just queries and insertions. You need to be able to do backups. You need to be able to recover from a crash. You need to be able to cope with the problem of some particular heavy query that's going and starving all the other queries from getting their work done. All those problems turn out to be the problems that if you do any of them badly, people won't buy you, and then, So I suspect that there's another factor of 10 to be gotten on this, over this data structure if you were to sort of sit down and try to say, how could I make it be the fastest possible thing? And someday that work will have to be done because the competition will have it and we won't, right? So let's see, what are some of the, I mentioned some of these just now. So some of the things you have to do in order to have an industrial strength dictionary are you need to cope with variable size rows. So instead of, we assumed for the analysis that the rows were all unit sized. In fact, database rows vary in size, and some of them are huge. Some of them are megabytes, or sometimes people do things like they put satellite images into databases. So they end up having very large rows. You have to do deletions as well as insertions. And it turns out we can do deletions just as fast as insertions. And the idea there is basically, if you want to do a delete, you insert the thing with a bit on it that says, hey, this is really a deletion. And then whenever you get a chance, when you're doing a merge, if you find something that has the same value, you just annihilate it. And eventually, when you get down, the delete has to keep going down because there might be more copies of it further down that were shadowed. And eventually, when you finally do the last merge, that tombstone goes away. You have to do transactions and logging, and you have to do crash recovery. And it's a big pain to get that right. And a lot of companies have foundered when they tried to sort of move from one mode to the other. How many of you have experienced the phenomena that your file system didn't come back properly after a crash? See the difference in age here. They're all using file systems that have transaction logging underneath them, right? When's the last time it happened? Tuesday. So the difference is you're paying attention and they're not, right? What? Disk failure. Yeah. That's a different problem.
Caching is not fine.
Yeah, so everybody's running with their disk cache turned on. And on some file systems, that's a bad idea. So, we're still suffering that it's been difficult to switch from the original Unix file system, which is 30 years old, and wasn't designed to recover from crash. You have to run FSCK, and it doesn't always work. We still have file systems that don't recover from crashes, so you can sort of see why that could be difficult. You have to, It turns out that one common use case is that the data is coming in sequentially, and this data structure just is, sucks compared to a Btree in the case where you're inserting things and the data actually is already sorted as it's inserted, because this is moving things all around and moving things all around. It's like, why didn't you, just notice that it's sorted and put it in? You have to get rid of the log-based B to get it down to log-based B of n instead of log-based 2 of n for search costs, because people, in fact, do a lot more searches than you have to. If you have to choose which to do better, you want to generally do searches better. And compression turns out to be important. I had one customer who had a database which was 300 gigabytes. He has a whole bunch of servers on it. Each server he had a 300 gigabyte database. And with us, it was 70 gigabytes because we compress. And we just do simple compression of basically large blocks. When we do IOs of like a megabyte. So when we take one of those megabytes, we compress it. And it's a big advantage to compress a megabyte at a time instead of like what a lot of Btrees, they have maybe 16 kilobytes. And gzip hardly gets a chance to get anywhere when you only have 16 kilobytes. It gets down to 12 kilobytes. But if you have a megabyte to work with and you compress it, particularly if it's sorted, right? So this is a megabyte of data that's sorted, so compression works pretty well on sorted data. So you get factors of 5 or 10 or something. And so we asked him to dump the data without the indexes, so just the primary table with no indexes, and then run that through gzip, and it was 50 gigabytes. So the smallest he could store the raw data was 50 gigabytes, and we were giving him a useful database that was 70 gigabytes that had a bunch of indexes. So he was like, yeah. And you have to deal with multi-threading and lots of clients and stuff. So here's sort of an example. We worked with Mark Callahan, who was at Google at the time. He's now at Facebook, on trying to come up with some benchmarks, because none of the benchmarks out in the world sort of do a good job of measuring this insertion performance problem. So IBench is an insertion benchmark, and basically what it does is it sets up a database with 3 indexes, and the indexes are random. So it's actually harder than real workloads. This workload, you basically have a row, and then you create a random key to point into that from 3 different places. Real databases, it turns out, probably have more of a Zipfian distribution. Have you talked at all about Zipfian distributions or of data? So this is sort of an interesting thing. If you're doing this kind of, you're dealing with a real world and caches, you should know that data ain't uniformly randomly distributed. That's a poor model. So in particular, suppose I have memory and disk, and this is 10% of the disks. Very simple situation. Very common kind of a ratio. You'll see this is how Facebook sets up their databases. 10% of the machine is that they'll have a 300 gigabyte database and 30 gigs of RAM. If the queries that you wanted to do were random, it wouldn't matter what data structure you were using. Let's suppose that God tells you where it is on disk, so you don't have to find it. You just have to move the disk head and move it. If they're random, then basically, no matter what you've done, 90% of the queries you have to do are going to do a random disk I/O. 10% are going to already be there because you got lucky, right? So that is not reflecting what's going on any workload that I know. What they'll see is more like 99% of the queries hit here and 1% go out here, or maybe 95% here and 5% go to out there. And it turns out that for a lot of things, there is a model of what's going on called a Zipfian distribution. So this would be a random uniform distribution. It's like every item has an equal probability of being chosen for a query. It turns out that for things like what's the popularity of web pages, or what's the frequency if you have a library, what's the frequency at which words appear in the library? So think words like the appear frequently, and words like polymorphic are less frequent, right? So So Ziff came up with this model, and this is a simple version of the model, in which says that the most popular word has probability proportional to 1. It's not going to be 1. It's going to be proportional to 1. The second most popular word is going to have half. The third most popular word is a third. And the fourth most popular word is a fourth, the probability of the first word, and so forth. All right, so if you plot this distribution, it kind of looks like this, right? It's like 1 over x. And what would you tell me if I told you that I had an infinite universe of objects that had a probability distribution like this? Does that seem plausible? Why? You're saying no. If you add them all together, it doesn't converge, right? So it's a heavy-tailed distribution. So it turns out that suppose you have, so if you sum up these up to 1, the sum from 1 to n of 1 over I, it's the nth harmonic number, and that grows over time. It's basically like the integral under this curve from 0 to, or from 1 to n. It's close to that. And what is the integral of that? It's like something you learned 7 years ago and now you've forgotten, right? You learned it when you were sophomores in high school or something. So it's approximately log of n. It's actually like log of n, plus 0.57 is a very good approximation for the nth harmonic number. When you're doing this kind of analysis, boy, it impresses people if you say, oh, that's h of n, and if you have 1 million items in your database, then the sum of all those things is h of 1 million, and what's h of 1 million? Well, the log of base 2 of 1 million, I know that, because I'm a computer scientist. So it's going to be like 20, and because we're doing log base e in that formula, maybe it's 15 or something. See, so if you have 1 million items, then the most popular item is going to you have to divide by h of n here. So the most popular item is going to appear 1/15 of the time, and the next most popular item is going to appear emergency backup chalk. Somebody's been burning both ends of this chalk. 1/30th of the time, and 1/45th of the time, and those add up when you go up to 1 over 1 million. Put another 0 in there, times 15. That finite series will add up to 1, approximately, except to the extent that I've approximated. So this is what's going on. So the most popular Facebook page, they might have a billion pages. So how does that change things? Well, that means the most popular one has probability 1 in 20, and the second most is 1 in 40. And this explains why cache works for this kind of workload. And nobody really knows why Facebook pages and words in libraries and everything else have this kind of this distribution, which is named after a guy named Ziff. But they do. Everything has this property, and so you can sort of predict what's happening. So IBench should have a Ziffian distribution, and it doesn't. So this is painting a worse picture or a better picture. It's making us look better than we really are, because the real world is going to have more hits on the stuff that's in memory for a Btree than this model, where basically you're completely hosed all the time because it's random. So this is an example in the category of how to lie with statistics, right? And it's a pretty sophisticated lie, right? If you're going to lie, be sophisticated. So these measurements were taken, and the top graph, the top up is good. It's how many rows per second we could insert. And this axis is how many rows have been inserted so far. And the green one is a Btree. It's basically, according to Mark Callahan, who's essentially a disinterested observer, it's the best implementation of a Btree ever. And you can sort of see what happens is as you insert stuff, the system falls out of main memory. And the performance was really good at the beginning, 40,000 per second, and then boom, you're down to 200 down here at the end by the time you've inserted a billion rows. Whereas for the fractal tree, it's, you know, you can sort of see this noise. That's because of some insertions are a little cheaper than other insertions, right? Some insertions, every other insertion is completely free, right? You had a free spot, you just put it in. 2 out of 4 insertions, you only had to, you know, 1 out of 4 insertions, you know, the ones that weren't free, half of them only had to do like a little operation in memory. So you see this high frequency noise of you know, because some things are cheaper than others. And that's, you know, like a factor of 30 or something. It turns out it even works on SSD, solid state disk. You might think, all this time I've been talking about disk drives. Solid state disk has a complicated cache hierarchy inside it. And we were surprised to see that basically we're faster on this workload on a rotating disk than the Btree is on a SSD, which is orders of magnitude faster in principle, but it turns out that for various reasons it's not. So you know, it's like one question I get often is sort of the world is moving away from rotating disk to solid state disk. A lot of applications. How many of you have solid state disk in your laptops? That's a really good application for a solid state disk because it's not sensitive to being knocked around, right? So it's worth it to have a solid state disk, even if it were more expensive, which it is. It turns out it's not that much more expensive for a laptop. It's a couple $100 more or something. But the advantage of it is that you go up in an airplane and you're sitting and trying to type in the middle of a thunderstorm flying across, and it doesn't care, right? Disk drives, you do that. Disk drives do not like flying at high altitude because they work by having a cushion of air that the head is flying on. And in airplanes, which are pressurized, the cabin to 8,000, to the same altitude as 8,000 feet, that's half an atmosphere. So there's only half as much air keeping it off. So if you travel a lot, that's when your disk drive will fail, is when you're flying. Okay, so it looks like, however, that rotating disk is getting cheaper faster than solid state disk is. So rotating disk is an order of magnitude cheaper per byte than solid state disk today. Maybe 2 orders of magnitude cheaper. It's hard to measure it fairly. But rotating disk, according to like Seagate, they're saying, oh, you know, by the end of the decade, we'll have 70 terabyte drives, you know, that are the same form factor. And so you figure out what the Moore's law is for that, and it's better than for lithography. Lithography is not going to be that much faster, that much more dense in that time frame. So at least for the next 5-10 years, it looks like disk drives are going to maintain their cost advantage over solid state storage, and maybe even spread that cost advantage. So for any particular application, for storing your music, SSD will be cheap enough. But for those people that have really big data sets, like these new telescopes they're putting up, these new telescopes are crazy. These people are putting up these telescopes. They're putting up 1,500 telescopes across the Australian outback. And each of those telescopes in the first 15 minutes live is going to produce more data than has come down from the Hubble total. And you know, there's just no way for them to, you know, I don't know what they're going to do, but it's a huge amount of data, and they're going to have to use disks to store whatever it is that they want to keep. And they don't like throwing away data because it's so expensive to make. So you know, if I were a disk maker, I'd make sure that my salesman had an office somewhere out there. So the conclusion is you're not going to be able to, at least for those applications, just have an index in main memory. You're going to have a data structure that works well on disk. The speed trends, well, seek time's not going to change. It hasn't changed. It's not going to change. The bandwidth of a disk drive grows with the square root of its capacity. So if you quadruple the storage on the disk because you've made the bits twice as dense in each dimension, then at one spin of the disk sees twice as many disks, not 4 times as many disks. So that projects out to something like disks that are 500 megabytes per second. So how long is it going to take to back up a 67 terabyte disk drive? So there remain, systems problems, and I was explaining to my son that there's all these problems in systems. Data structures aren't suited, and all these systems suck. He said, well, so isn't that horrible if you're a computer scientist? It's like, no. Because we make our living off of these problems, right? So here's some problems. There's plenty of living to be made yet. Power consumption is also a big issue for these things. If you fill up a data center, so a Google data center, a room which is probably bigger than this room, full of machines. The Facebook data center is probably a room about this size, full of machines, and power and cooling is something like half the cost of the machines. The machines, machines for something like Facebook might be, the hardware might cost them $10 or $20 million a year, and the heating and cooling is another $10 or $20 million a year, which is why they go off and they build these data centers in places like North Carolina, where I guess they're willing to give them power for free or something. So making good use of disk bandwidth offers huge power savings, because basically, you can use disks which are cheaper than solid state for power, and they also, you want to use that well. CPU trends, well, you've probably talked about this, right? CPUs, you're going to get a lot more cores. I actually have a 48-core machine that cost $10,000 that I bought about a month ago. And our customers mostly use machines that are like $5,000 machines. So when I provisioned this machine, I said, well, I should buy a machine that's twice as good as what they're buying, because I'm developing software that they're going to use next year. Right? So I bought a $10,000 machine, which is 48 cores, and we're having all sorts of making a living with that machine. The memory bandwidth and the I/O bus bandwidth will grow, and so I think these machines are just it's going to get more and more exciting to try to use all these cores. Fractal trees have a lot of opportunity to use those cores to improve, reduce the number of disk I/Os. So the conclusion is basically these data structures dominate Btrees asymptotically. So, and then Btrees have 40 years of engineering advantage, but that'll evaporate eventually. Fractal, these data structures ride better technology curves than Btrees do. And so I find it hard to believe that in 10 years that anybody would design a system using a Btree, because it's, how do you overcome those advantages? So basically, all storage systems are going to use data structures that are like this or something else. There's a whole bunch of other kinds of indexes that we haven't attacked, things like indexing multidimensional data, or indexing data where you have very large keys, very large rows. Imagine that you're trying to index DNA sequences, which are much bigger than a disk block. So there's a whole bunch of interesting opportunities, and that's what I'm working on. So any questions or comments, arguments, fist fights? Okay. Where is the mic? It's on my coat.
So actually, this is a very interesting point, because if you think where the world is leading, I think the big data is something that's very, very interesting, because all these people are gathering huge amount of data, and they are storing huge amount of data, and what to do with data, accessing them, is going to be one big problem. I mean, if you look at what people like Google are doing, and they're just collecting all those, nobody's throwing anything out, and ability to kind of look at them, analyze them, do cool things with the data is going to be very, very important. So I think that would be very interesting high performance end. Is not just doing number crunching. Until now, when people look at very high performance, it's about CPU. It's about how many flops per second can you do, teraflops, petaflop machines, and stuff like that. But I think one thing that's very interesting is not petaflops. How many terabytes of data can you process through to find something?
So I was at a talk by Facebook, and they serve 37 gigabytes per second out of the database tier. And that's that's a lot of serving. That's out of one little piece of whatever they're doing. Those guys have like 3 or 5 petabytes. And in the petabyte club, they're small potatoes. There's people who have hundreds of petabytes. People with 3-letter acronyms.
I mean, some of those 3-letter acronym places, the amount of data they are getting and they're processing is just gigantic.
Yeah.
And I think to a point that even some of the interesting thing about if they keep growing their data centers at the rate they kept growing, in next couple of decades, they will need the entire power of the United States to power the data centers, because they are at that kind of things at this point. I mean, what they're saying in the next, even in these big national labs, the reason they can't expand is not they don't have money to buy the machines, but they don't have money to pay for electricity, and also they don't have electricity, that much electricity anywhere near them to basically feed it.
I've run into people for whom the power issue was a big deal. I look at it and say, you bought a $5,000 machine, you spend $5,000 in power over the lifetime of the machine, and it doesn't seem like it's that big a deal. But they've filled up their data center, and the cost of adding one more machine has a huge incremental cost, because they can't fit one more in, right? So that means they have to build another building, and so almost everybody's facing that problem who's in this business. If they and then they try to build a building somewhere where there's natural cooling. Google's written these papers about, it turns out if you don't air condition your computers, most of them work anyway. So, well, air conditioning is a quarter of the cost over the lifetime of the computer. So if you can make more than 3/4 of them give you service, you're coming out ahead.
On that note, MIT is part of a consortium that includes Harvard, Northeastern, Boston University, and University of Massachusetts Amherst to relocate all of our high-performance computing into a new green data center in Holyoke, Massachusetts. So the idea is that rather than us locating things here on campus where the energy costs are high and we get a lot of our energy from fuels that have a big carbon footprint, locating it in Holyoke, they have a lot of hydropower and nuclear power there, and they're able to build a building that is extremely energy efficient. And it turns out that a bunch of years ago, when they were digging up the Route 90, the Mass Pike, they laid a lot of dark fiber down the length. And so what they're going to do is light up that fiber, which comes right back here to the Boston area. And so it'll be, for most people who are using these very high performance things, it doesn't really matter where it's located anymore at the level of that. So instead of just locating some piece of equipment here, we just will locate it out there, and the price will drop dramatically, and it'll be a much greener way for us to be doing our high-end computing. Yeah, question?
Isn't someone talking about water-cooled offshore floating data centers?
Sure. So water-cooled, question is, are people talking about water-cooled offshore floating data centers? Yeah, I mean, locating things, in some area where you can cool things easily makes a lot of sense. Usually they tend to want those near rivers rather than in the middle of the ocean, just because you get the hydropower. But even in the ocean, you can use currents to do very much the same kind of thing. So for some of these things, people are looking very seriously at a whole bunch of different strategies for containing large-scale equipment.
So one thing that's very counterintuitive is people are trying to build data centers in the middle of deserts when it's very hot. I mean, why do you think people want to build a data center in the middle of a desert? Solar power is one thing. No, it's not solar power. No, that's not really cold enough. That's not it.
Cheap property.
No, the biggest thing about cooling is either you can do air conditioning where you are using power to pull heat out, or you can use just water to cool. And what happens is most of other places is the humidity is too high. And when you go to the desert, humidity is low enough, then you can just pump water through the thing and get the water evaporation going by, and then use that to cool the system. So sometimes they're looking at data centers in places where it could be 120 degrees, but very low humidity. And they think that is a lot more efficient to cool than that. So there are a lot of these interesting non-intuitive things people are looking at. So what they say is humidity is the killer, not the temperature.
If you locate it on the South Pole, then that's, both cold and really low humidity.
Yeah, so I mean, it'll be interesting to see how these things develop. It's a very so-called hot topic in these days is, energy for computing. And it matters, the energy for computing, of course, matters also not only at the large scale, but also at the small scale, because you want your favorite handheld to use very little battery, so your batteries last long. So the issue of energy, using that as a measure, we've mostly been looking at how fast we can make things run in this class, but many of the lessons you can use to say, well, how can I make this run as energy efficient as possible? Okay, and just as and what you'll learn is that many of the lessons we've had in the class during the term, we focused, as I say, on performance, but there are many resources in any given situation that you might want to optimize. And so understanding something about, how do I minimize energy? How do I minimize disk IOs? How do I minimize clock cycles? How do I minimize off-chip accesses, which tend to be much more energy intensive than on-chip? All those different kinds of measures end up being part of the mix of what you have to do when you're really engineering these systems.
So I think another interesting thing is, because we are in this time where things grow, some stuff grow at exponential rates and stuff like that, some of those ratios that made sense at some point just suddenly start making really bad things. Like, for example, in disk. I mean, at some point, the seek times were normal enough that you didn't care. And at some point, because the rest of the things took off so fast, and suddenly it becomes this really, really big bottleneck. So
Btrees were a really good data structure in 1972. Because, well, the seek time and the transfer time and the CPU, the CPUs actually couldn't read in the data in one rotation. So people didn't even read consecutive blocks because the CPU just couldn't handle the data coming in that fast. You would stagger blocks around the disk so that when you did sequential reads, you'd get this one, and then this one, and then this one. There was this whole thing about tuning your file system. It's like...
By the way, back when disks were...
Yeah.
even
washing machine.
Washing machine size.
For 20 megabytes.
Oh yeah, that's a big disk. So hopefully you guys got a feel for, we have been looking at this performance on a small multi-core and stuff like that, how it can scale in different directions and kind of impact performance can have in there. And in fact, if anybody has read books on why Google is successful, one of the biggest things for their success is they managed to do huge amount of work very cheaply, because the amount of work they do, if anybody else did in the traditional way, they can't afford that model to give it for free or give it for, supply it for advertising. Because they can get it done because it's about optimization. So get the performance, basically relates to cost, and if the cost is low enough, then they don't have to keep charging huge amount of money for each search.
So I think let's thank Dr. Kuszmaul for excellent talk, and can you hang out for just a little bit if people
Sure.
want to come down? Okay, thanks.